Hello folks, this question is about Archimedes principle, buoyancy and so on in the air. It's about a hot air balloon, and I draw a hot air balloon here in my ugly picture, and I'll go ahead and read the question to you. The envelope of a typical hot air balloon has a volume of 2500 meter cubes, so the volume of this hot air balloon is 2500 meter cube. Assume that such balloon is flying on Fort Collins, Colorado, where the density of the air, so we know the density of the air here, that'll be our raw fluid, right? 1 kilogram per meter cube. And I'm going to remember right away a buoyancy force is defined as our raw fluid times V submerged, well, G, rho G, V submerged, mass of the displaced fluid, and G as always is the acceleration due to gravity, 9.8 meters per second squared. So let's see what the question's asking us. A, what mass of air does the balloon displace? That would be mass of displaced air equals to density of the air times the volume submerged in this case, or displaced. So all of the balloon is submerged in the air, it's all in the air, so this submerged volume or displaced volume is equal to volume of the balloon, and that's it. And remember, in here density is equal to mass divided by the volume. And if we are looking for mass from here, we can just multiply these two. Mass will be equal to density times the volume. This is for anything, and we apply it to this displaced air. And find how much air is displaced. Density of the air is 1 kilogram per meter cube. And we'll multiply this by the volume of the balloon, which is equal to the displaced air here, so 2500 meter cubes goes, we are left with mass of the air or displaced air will be 2500 kilogram. That's A. B, if heated to a maximum temperature, so we again heat this balloon and decrease the density of the air inside. The air inside the balloon has density about 0.80% that of the surrounding air. So we, not we in, rho in 80%, that's 0.8 times rho air in regular value, and rho air is 1, so 0.8 times 1 kilogram per meter cube. If we are looking at 80% of something, that's how we calculate it. You guys perhaps know. If you don't, that's how we calculate it. We multiply the value by 80 over 100, and that's going to be 0.8. And that will be 0.8 kilogram per meter cube. So less density, if an object in the air is less dense than the air, it will be going up. So this will cause the balloon to go up and become in equilibrium again. So the density inside will be 0.8 kilogram per meter cube. And what is the question asks is, what is the mass of air in the balloon? Now V in still will be equal to V, so 2500 meter cube, and we'll find the mass inside using again rho in, V in. 0.8 kilogram per meter cube times 2500 meter cube. And this will give us a mass of 2000 kilogram. Right. how much mass can the balloon lift? This is actually part C, the most important part in this question. How much mass can the balloon lift? That's going to be in equilibrium. The balloon has its own mg, so let's call the balloon of mass of balloon m. It will have its own weight, and additionally how much extra mass we can add to it. Let's say some people here, and I'm going to call this m add. So we'll have down m added times g, and what we will have up lifting up the balloon will be the F buoyancy, right? So if it's able to lift this mass, we'll just use equilibrium. Up forces equal to down forces. So this buoyancy will be able to lift up all the mass. I'm going to say F buoyancy is equal to mg of balloon plus added mass times g. And that's the idea. So the question is asking me what is that mass that I can add to balloon. If I add too much, it will be going down, so I don't want to go do that. I want to calculate how much mass I can add. So if you are going to ride a balloon or operating a balloon, you will have to take this into account. I'm going to go ahead and solve for m add first here for added mass, and then I'm going to put in the numbers. We have all the numbers given. First I'm going to take this guy to the other side, rearrange, leave this guy on the left hand side. So I'm just swapping the equation here. I'm going to have m add times g is equal to buoyancy force minus mg. That would be for the balloon again. And divide each side by g. I'm going to find my mass added. So the maximum amount of mass I can add is equal to F buoyancy minus mg divided by g. And now I'm going to put in the numbers and solve for my added mass. I have to find the buoyancy force. Right here, and the rest are known, and I know if buoyancy is equal to always rho of fluid submerged volume times g. Rho of fluid is rho air in here. V submerged is the V balloon times g. That will give me the buoyancy force. Rho air will be, of course, outside air, 1 kilogram per meter cube. Not the air inside here, right? That's part of the balloon. Times the submerged volume, the whole volume of the balloon, and g is g 9.8 meters per second squared here. And this will give me an F buoyancy of 24,500 Newton. So insert all these in here. I can find my m added mass, and I'll find that the maximum mass I can add is equal to 500 kilogram. So about 3, 4 people, maybe 1 child, I can add in here. It'll be safely going. Otherwise, I have to maybe heat the gas more here to make the air less dense, so I'll have easier lift from the air. Okay, this idea of increasing the volume, decreasing the density is used in the marine life. Fish use it to increase the volume of their bladder to swim easily. Manatees use it as well by getting air into their lungs. This question is about a fish with swim bladder deflated, so not increasing the volume of the bladder. The fish has 9.5 kilograms, so mass is 9.5 kilogram. Has a density of 1050, so raw fish, let's call this 150 kilogram per meter cube. And it's swimming in the ocean. The density of the sea or ocean is slightly different than water. It's generally salty, and it's 1030 kilogram per meter cube. And I'm just going to check the number there. Yes. What volume of gas must the fish have in its swim bladder to achieve neutral buoyancy? Neutral buoyancy means densities are equal, so we want raw fish to be equal to raw sea. That means we want the density of the fish to drop down to 130 kilogram per meter cube, and it will be easier for fish to swim if it can manage to have that density. So here's what we're gonna have. Density of the fish, maybe call this raw fish 2, right, and call this raw fish 1. It's gonna change. Raw fish 2 will be equal to mass of the fish. It will not change. We ignore the mass of the gas here. Divided by initial volume plus added bladder volume, right? And from here we can solve. If we know the initial volume, mass, we know the final density, we can solve for how much volume the bladder should have. Now, can we find this initial volume? Yes, because we have here the mass, fish, we know the density of the fish. In the initial case is equal to mass divided by the volume. So we'll get that volume from here, simply switching these two. As I always mention to you folks, is possible. So volume will be mass divided by the density of the fish. 9.5 kilogram divided by 1050 kilogram per meter cube. And that will be equal to a very small number, which would what we would expect, 0.00905 meter cube. I'm going to keep all the decimals here for a correct, close to correct answer. Now we input this in here. We know mass, we know final fish volume. We'll solve for the bladder. I'm going to go through the algebra slowly here for those who get confused about algebra always. First I'm going to switch these two numbers, the whole denominator and raw fish. So I'm going to have this V plus the added bladder volume is equal to mass divided by raw fish. That's the density of the fish in the second case, where we're going to change it to the C, right? He wants to change it to the C density. So this will be 1030 kilogram per meter cube. Now I'm going to leave V bladder alone. To do that, I take this guy to the other side. It's plus here, goes as minus. So after that step, here is what I'm going to have. V bladder is equal to mass of the fish divided by density of the fish in the second case, fish 2 minus V. Now I'm going to enter everybody to solve for how much more bladder volume the fish should add, how much more gas it should add inside to change its density from 1050 to 1030, so it can freely swim in in the ocean. And calculate that. I'll leave that to you folks. Just put in the numbers. 9.5 kilogram. 1030 is what I want. Kilogram per meter cube. Minus the volume initially 0.00905 meter cube. And after you do this, you should find this given number here. So we will ladder from there. Should be equal to 0.00017 meter cube. Nothing is small. That small change helps the fish to swim in the sea more comfortably. So it's important.